Hi, it's Mrs. V here, and today we are going to talk about the properties of covalent network substances. So we're going to cut to the PowerPoint and get straight on with it. Let's look at covalent network substances. In our previous lessons, we've looked at covalent molecular substances, but that's not the only type of structure that a covalently bonded substance can have. They can also form covalent network lattices. So our learning intentions for today, you will be able to describe the structure of both 2- and 3-dimensional covalent lattices, and you'll be able to relate the properties of those substances to their structure and to their bonding. And we'll learn about some technological advances that are available to us using covalent network substances. Covalent solids. We've learned before that you can get a solid molecular substance by having a lattice of molecules, but a covalent network substance is different. A covalent solid forms when a covalent bond happens between two atoms by sharing electrons. And within the lattice, each atom forms covalent bonds with its nearest neighbour or neighbours. Okay, often this happens with several atoms, which is how you get the extended lattice. It's essentially just one big molecule with covalent bonds throughout it. And you can get these lattices in 2 dimensions or 3 dimensions, and we're going to look at examples of both. So looking at the properties of solids, we're looking at the bottom row here, the covalent network solids. So the bonding within that solid is covalent. The properties, they have very high melting points, they're very hard, and they don't conduct. Let's have a look at why that might be. So they're extremely hard. In order to break a covalent network lattice or displace part of the lattice, you're going to have to break covalent bonds, and they are the strongest primary force. So that's going to be pretty darn hard to do. And in fact, covalent network substances are some of the hardest substances that are known. So things like diamond, we have a picture of the structure of diamond there, and you can see that each carbon atom in that structure is bonded to covalently to 4 other carbon atoms. It's still considered to be the hardest known substance. It gets a 10 on the Mohs scale, and it actually defines the top end of the Mohs scale. However, there is another form of carbon that might be harder. Diamond's used in industrial cutting blades and drill bits, and it's used to polish other stones, and of course you know it's used in jewellery. But its hardness is due to the fact that if you want to break a piece off, you've got to break covalent bonds, and they're super strong. Another example, cubic boron trinitride is a covalent network lattice substance. It's actually the 2nd hardest substance after diamond, or it might be displaced down to 3rd. It's used for industrial cutting tools, it's used for industrial abrasives, so sanding blocks, and it's also extremely hard because to break a piece off, you've got to break covalent bonds. And remember, covalent bonds, the strongest. There's silicon carbide. Silicon carbide has the same structure as diamond, but each alternate atom is a silicon atom, so it's a mixture of silicon and carbon. And this gives the silicon carbide semiconducting properties, so it's very useful for making semiconductors that can operate at very high temperatures. Okay, it's also used in industrial abrasives and cutting tools. So covalent network substances don't melt because they're just one giant molecule. If you actually added enough energy to break all the covalent bonds, they'd all break at once and the whole lattice would just decompose into its elements. So if you have a diamond and you give it enough energy, you can actually decompose it into carbon dust. I would not suggest you try this at home though. I don't think you'll be very popular. Covalent network substances don't conduct electricity. We will look at some notable exceptions later in this presentation, but generally they don't conduct electricity because, of course, you know, to conduct electricity you need mobile charged particles. Covalent network substances have no ions, and all the electrons are localized in their covalent bonds, so they can't move around. And that means there's no charged particles able to move and create current. We're going to go and look at the allotropes of carbon. Now, allotropes is a word you may not have heard before. Allotropes, it just means different physical forms of the same element. So the same element has two different forms. So things like oxygen exists as O2, which is oxygen, but also O3, which is ozone. There are different forms of sulfur as well. So we're going to look at the allotropes of carbon. Allotropes have different chemical structures and they have different chemical physical properties. So when I was just a young chemistry student at school, carbon only had two allotropes. Carbon only had diamond and graphite. There was nothing else. These days, we've discovered so many different forms of carbon. There's diamond and graphite. There are the fullerenes, the buckyballs, lonsdaleite. There's amorphous carbon nanotubes, glassy carbon, carbon nanofoam. There's even more. I imagine as technology moves on, we will find even more allotropes of carbon. And some of these new allotropes that have been found are incredibly useful in technology. So here's some diagrams showing the structures of these different forms of carbon. And you can see that they're all composed of only carbon atoms, but the way that they are linked together by their covalent bonds are very different. They have different patterns. Some are three-dimensional, some like graphite are two-dimensional layers. You can have, if you have a single layer of graphite, that's what we call graphene. And we have some, just the buckyballs, C60 and C70 there, are reasonably small units of carbon. Carbon nanotubes, it's just a sheet of graphene that's rolled around into a cylinder. Then there's amorphous carbon that doesn't really have that beautiful repeating pattern that allows it to be a crystal. So graphite has some very interesting properties, and we're going to look at how graphite's properties relate to its bonding. So graphite's shiny. It has a really metallic sheen. Graphite's very soft and slippery. In fact, your pencil lead is made of graphite, and all it takes is for you to press that pencil lead onto paper and you wipe stuff off. So graphite's not very hard at all. It's very easy to displace part of the graphite lattice. It's very slippery. In fact, it's used as a lubricant. You can buy graphite as a lubricant. And if you've got a zipper that's not working particularly well, or a key lock that is a little bit stiff, if you actually scribble some graphite onto your zipper, or you scribble some graphite onto your key, you'll actually lubricate it and it'll work much better. Graphite conducts electricity as well. In the center picture there, we see a picture that has been just scribbled onto paper with a graphite pencil. And if we put a battery at one end, we're actually operating a little LED, and just with the electricity flowing through the graphite on the paper. I actually saw a few very cool videos about doing that while I was researching some of the uses of graphite. So the structure of graphite is that it exists in these two-dimensional layers. And in each layer, you can see that each carbon atom is bonded to 3 other carbon atoms, and that forms a planar structure. There are weak secondary forces holding the layers together, and that's why it's soft and slippery. You're not actually breaking up that layer of carbon atoms because that's held together by strong covalent bonds. What you're actually doing is just sliding the layers off of one another, and that happens really easily because it's only those weak secondary forces that are breaking. So why can graphite conduct electricity? Well, if you look at carbon, carbon actually has 4 valence electrons, but in graphite it's only making 3 bonds, which means there's 1 electron left over. And that electron is able to become delocalized and move through the layer. And of course, delocalized electrons, we learned when we were studying metals that delocalized electrons could move when you applied a potential difference, and that could establish an electric current. And that is why graphite is a good conductor of electricity, because those delocalized electrons are able to move through the layer. It has a metallic luster. If you scribble your graphite onto a bit of paper, it's reflective in the same sort of way that a metal is reflective. It has a metallic luster. And you may remember that metals were shiny because they have delocalized electrons, and those electrons can absorb and re-emit visible light. Well, graphite also has delocalized electrons, and so those electrons can also absorb and re-emit visible light, and therefore graphite has a metallic luster in the same way that a metal does. Graphene. If you take a single layer of graphite, then you have a material known as graphene. And graphene is what's called a nanomaterial. And it has the prospects of some very, very exciting uses. It's strong. Why would it be strong? That's right, covalent bonds throughout the layer, very hard to break, so it's extremely strong. It's flexible, however, because it's a very, very thin material. It's on a nanoscale, 1 atom thick. So very, very flexible. It being so thin also means that it's transparent. Plus, it's a great conductor of heat and electricity. Why would it conduct heat? Because the mobile valence electrons, the delocalized electrons, they can transfer kinetic energy throughout that lattice. So it has great potential for use in electronics on a nanoscale. That's all we're going to talk about for today. So I will see you in the next video.